Good morning, everyone. Today we will continue with numerical methods for solving unconstrained optimization problems. And today we will cover the so-called gradient-free method. So just to remind everybody, we would like to minimize a certain objective function, which is denoted by f here. X are the decision variables, and we would like to minimize this function, meaning we would like to find the value of x where this function achieves its minimum. And this minimal value is then denoted by j star, and the point in which the minimum will be achieved will be x star. That would be the optimal solution. And in previous lectures, we have seen how to use either the analytic solution to this optimization problem, where we took the gradient of the function, we set the gradient equal to 0, and then we have solved the system of equations to find the optimal point. However, we have also seen that this method is only applicable if the system of equations that we need to solve is simple. In the ideal case that that gradient is linear in the decision variables. Then we can easily find the stationary point, and then we can use the Hessian to decide whether the stationary point is a minimum, a maximum, or a saddle point of the objective function. If the gradient is nonlinear in the decision variables, but it is still available, then we have seen in the previous lecture how to use the gradient-based method. And today we will see how to solve the optimization problem when the gradient is not known analytically, meaning we basically don't know the gradient. And we will see how to use gradient-free methods to still obtain the optimal solution. But before we start, as usual, we will have a short test to cover what was already told in the previous lecture. So a couple of questions. So the first one is, those gradient-based methods, which use the gradient to essentially find the search direction and then go in the direction of the negative gradient when we are minimizing, is this a local method or a global method? Well, first of all, what does it mean whether a method is local or global? If somebody says, I have a local method for minimization, what does it mean?
Find the minimum. Might be a local.
Exactly. So a function can have multiple minima. Some of them can be local, some of them global. So a local method is not guaranteed to find the global optimum. So and then a global method guarantees finding the global optimum. So these gradient descent methods, are they local or are they global? So they are local, right? Because we can arrive at a local optimum. Okay? Next question. Is it true or false that in the descent method, the initial choice of parameters is not so important? Is it true or false? And again, this is connected to the previous question. So there are two possible answers here. There is a case where the choice is pretty much irrelevant. What is the choice? Right, so if the function to be minimized is convex, then it doesn't matter too much where we start. Now, what does it mean, doesn't matter too much?
Well,
doesn't matter with respect to what?
Number of iterations we need to do to achieve the optimal.
So you are saying that the number of iterations is irrelevant of the starting point? Okay, so the number of iterations still depends on the position of the starting point, but what does not depend on the starting point is whether we converge to a global optimum or to a local optimum, because we know that a convex function only has a global optimum. Okay, it might have several optimal points, but each of them would be equally good. Okay, so to this respect, it doesn't matter too much whether we choose a starting point of a convex function with respect to finding the global optimum, but it does depend when minimizing a non-convex function. Okay? then obviously, depending on the starting point, we might converge to one of those local optima. Okay? So in general, it is false that gradient-based methods would not depend on the position of the starting point. Starting point is important when minimizing non-convex functions. Okay? Next one. Imagine we would like to minimize some function, for instance, a non-convex function. Is it true that if we start closer to the global optimum, so here, the global optimum, the point where the function achieves its minimum is here. Now, let's imagine we have two starting points, one red point and the green point. The red point is closer to the global optimum. Is it true that if the starting point is closer to the optimum, then we will converge to the global optimum faster than from this point? Is the distance an indicative of how quickly we will converge? Well, again, in convex functions it is, but not in non-convex functions, because here the gradient-based methods would drive this point in this direction, because that's where the gradient points, okay? Well, the negative gradient, okay? So even though this point is quite close to the global optimum, we will actually never converge to this point because the method would be stuck in this local optimum. Okay? So in general, this answer is false. For general functions, it might be true for convex functions. And in previous lectures, we have seen basically two gradient-based methods. One was the gradient descent method, and the other one was the Newton method. And we said that the Newton method usually exhibits a lower number of iterations when converging to the optimum. So now the question is, imagine I have the same function that I want to minimize, and the Newton method takes 5 iterations, and the gradient-based method takes 100 iterations. Now, the runtime of these two methods, would it be true that the Newton method is faster in absolute time than the gradient-based method? Why not? Precisely. In the Newton method, what we need to do in every iteration is to compute this expression where we take the Hessian and we have to invert the Hessian. While the gradient-based method only has the gradient here. So essentially this multiplication by the inverse of the Hessian is not present in the gradient-based method. And we know that inverting a matrix is actually not an easy task. It takes some time. In general, it takes something like n cubed operations, where n is the dimension of the matrix. Okay, so just the total number of iterations is not directly comparable. This is also something we have talked about in the previous lecture. Imagine we would like to minimize a convex quadratic function. How should we choose the step size in the Newton method to achieve the lowest possible number of iterations? And the lowest possible number of iterations is 1. Okay? So how should we choose the step size to actually achieve the global minimum of a convex quadratic function in exactly 1 iteration? Do you remember that? What was the value of the t? T was the step size. Yeah. And we have seen the proof which says, okay, if it is a convex quadratic function, then we can actually find the minimum analytically. And then we simply solve the system of equations for t, and from that we will see that t must be equal to 1. Okay? So convex quadratic functions are actually very easy to minimize using the Newton method. However, if we would like to apply the Newton methods, we need to know the gradient as well as the Hessian, which is the same as solving or using the analytic method. Okay? So what we want to say here is that the Newton method for convex quadratic functions is basically equal to the analytic solution of the unconstrained minimization. Okay? Next question. Imagine we have a function where we have 10,000 decision variables. And I might even add here that imagine that the function is quadratic, convex quadratic function. And we know that for a convex quadratic function, the Newton method converges in exactly one iteration. Would you choose the Newton method to find the minimum here, or rather the gradient-based method?
Gradient.
Why?
Because to invert 1000 by 1000 matrix, it will take much more.
Right, so just try it on your own in MATLAB, generate a matrix 10,000 by 10,000, and just ask MATLAB to invert this matrix. If it doesn't run out of memory, then it will take quite some time, meaning seconds, maybe minutes, to invert this matrix. While the gradient-based method will converge, I mean, it might take hundreds to 1,000 iterations, but each of the iterations will be like 1 millisecond or maybe 1 microsecond, okay? So the gradient-based method would converge here in something like 0.0 something seconds. While the Newton method, even though it would need to perform a low number of iterations, ideally just one iteration, it would be much slower, okay? And here is, well, again, it's due to having to invert the Hessian, which is of significant complexity. Okay, next one. The same scenario, but this time the number of decision variables is only 10, and the question is the same. Would we rather pick the Newton method or the gradient-based method? And actually we might add some conditions here, because actually this problem is not kind of well posed to answer this question. So under which conditions would we pick the Newton method over the gradient-based method? So first of all, would we even consider the Newton method? Yeah, inverting a 10 by 10 matrix is not a big deal, okay? So the Newton method would be the preferred way. And again, for the same reason that this inversion here is now rather simple. However, there is something missing from the problem definition, which, if not satisfied, actually doesn't allow us to apply the Newton method at all. In which case, the gradient-based method might be the only option. Right. And it has to exist in the first place. So when does a Hessian exist? What is the property of the objective function which says the Hessian will exist for every point? Eigenvalues, okay, there is a more general property which says the Hessian, meaning the second derivative, will exist. How do we call a function for which second derivatives exist for every point in the domain of the function? Not just that. There are non-convex functions for which the second derivative still exists for every point. Sorry? That is a special case. For instance, the function x cubed is not quadratic and the second derivative still exists. That's still only a special case. X cubed is a non-convex function and still it has the second derivatives defined.
Order of equation?
Which order?
Second order.
Yeah, so it has to be twice differentiable. Okay? And what we also require is that it's twice continuously differentiable, meaning that the second derivative doesn't suddenly jump from one point to the other one, meaning essentially there are no discontinuities in the function. Okay? So if the function is twice continuously differentiable and the number of decision variables is low, then we prefer the Newton method.
We can prefer according to our application.
Definitely, yes. Yeah. Yeah, it all depends what are our constraints on the computational power, whether we can afford inverting the Hessian or not. Yeah. There are like embedded hardware platforms where the computational power is not high enough to actually even invert the Hessian, in which case we would need to apply the gradient-based method. Okay. Here is a tricky question. Imagine we would like to minimize an affine function. The question is, can we use the gradient descent method to find the minimum? And again, it has something to do with continuous differentiability of the function being twice continuously differentiable and so on. So can we use the gradient-based method? Remember, the gradient-based method is an iterative procedure where we, to the current point, add the minus value of the gradient multiplied by t. So if the method has to be applicable, the gradient must exist. Does it exist always for every x? What is the gradient of a scalar affine function ax plus b? What is the derivative of this function? A. That's the gradient. And a doesn't depend on x. Okay, so this function is always differentiable. Therefore, the gradient-based method is just this here, okay, where t is the step size. So the gradient-based method is, in theory, applicable. The question is, do we want to solve the problem using the gradient-based method? Okay, so question like this. After how many iterations will the gradient descent method converge when minimizing an affine function ax plus b? After how many iterations will it converge? And there are kind of two answers here, depending on some property of the objective function. So what happens if a here is equal to 0? So we just have a constant function. After how many iterations will the gradient descent method converge, if at all? Okay, so the iterations are like this. X plus is equal to x minus t times a. Okay? That's the gradient descent iteration for an affine function. So what we are saying now is, imagine scenario 1 where a is equal to 0. What are the iterations then? Simply x plus is equal to x. Okay? And we also know that there are some termination criteria, and one of them could be, for instance, that the distance between the current point and the point at the next iteration is smaller than some epsilon. Other criteria might be that the function values at 2 consecutive iterations satisfy this property. And finally, the condition might be that the gradient of the function at the current point is less than epsilon. Okay? And we know that the gradient is just a, which in this case is equal to 0. Okay? So actually, in all 3 possible stopping criteria, they will terminate in exactly 1 iteration, okay? Which essentially meant we already have been at the optimum. Okay? I mean, this is kind of a tricky question. I mean, it's not too realistic, but it shows that there are also some theoretical properties which can be analyzed with respect to a particular function. Okay, so that was the first case where a is equal to 0, and now let's suppose the other cases where a is not equal to 0. Where is the optimum? What is J star as minimization of ax plus b, where x is unconstrained, meaning it can take any values? Plus or minus infinity, depending on the sign of a. Okay? So after how many iterations will this procedure terminate if a is non-zero? Right. So in theory, it will take infinite number of iterations. Why? Because if we are considering that a is not equal to 0, then for any positive step size, and the step size has to be positive, okay, So essentially, this term here is always either positive or negative, which means that the next iterate is always larger than the previous iterate in the absolute value, okay? And then unless this product is smaller than epsilon, then we will continue iterating indefinitely, okay? Which shows that the gradient-based methods are not ideal for this task. Essentially, this task is not well posed because minimizing an affine function without constraints either is the minimum is at minus infinity, plus infinity, unless a is equal to 0. Okay? So this question only has some concrete meaning when we add constraints. Then suddenly this becomes a valid problem. Okay, next one. Imagine the same affine function. Can we use the Newton method to find the minimum? Why not? What is the Hessian, the second derivative of the affine function? It's just 0. And in the Newton method, we would need to invert the Hessian, and the inversion of 0 is undefined. Okay? So this shows that the Newton method doesn't work for affine functions. Okay, next one. So far, we have talked about minimization of functions. And we have seen what is the general rule for the iterations of gradient descent method. But that was for the minimization of the function. How can we modify the general procedure to achieve a maximum of certain function? So again, x plus in the gradient descent methods is the previous iteration minus, or rather plus t times the minus value of the gradient. Okay? But this has achieved the minimization of f. How should we modify this updating rule to achieve maximization of f? So essentially here, instead of the minus, we would need to put a plus. Okay? So we need to go in the direction of increase of the function. Okay? So remember, when we had a function like this, then essentially in the minimization, we took the gradient, and the gradient was the tangent here. It says when we increase x in this direction, the function will increase. And since we wanted to minimize, that's why we required a minus sign here. We had to go in the opposite direction. So for maximization, we simply go in the direction in which the gradient points. Okay? So that's here. Okay, so when talking about maximization, which property does the function to be maximized has to satisfy in order for the maximization to be a convex optimization problem? Essentially, which function has the maximum being the global maximum, all maxima being global? How do we call a function in which all maxima are global? That's a concave function. So the function to be maximized has to be concave in order to be or to obtain a simple problem. Can we apply the Newton method to maximize a concave function? So the gradient method for sure, but what about the Newton method? Is the Hessian of the objective function positive definite? So we have a concave function, okay? And we are maximizing that function. We know that for the Newton methods to be applicable, we would like to have the Hessian to be positive definite. But we know that the Hessian of a convex function is positive definite. So what about here? Can the Newton method be applied?
We can see convex.
Right, so when did we require the Hessian to be positive definite? When minimizing a convex function. But now we are maximizing a concave function. How can we equivalently find this point here? we can flip the function. Okay? So if this is f of x, we can flip it along the x-axis to obtain the minus f of x function. And then we can minimize this function instead. Okay? And these 2 points will coincide. So the function where minus f of x has the minimum, so if we denote by x star the point where the function minus f of x has the minimum, so that's the argument which minimizes the function, then it's the same as the argument which maximizes the function f of x if the function, well, actually this holds for any function, but here we are assuming that this function here is concave. Okay? By the way, when we said that the convex function has a positive definite Hessian, what is the Hessian of a concave function? It's again, just flip it. So a Hessian of a concave function is positive definite. Okay? Sorry, negative definite. Okay? So when we flip a negative definite Hessian, we obtain a positive definite Hessian, and we can minimize it. Okay? So the answer here is that the maximization of a concave function is the same as minimizing minus that concave function. Okay? Minus a concave function is a convex function which has a positive definite Hessian, so we can minimize it, meaning we can apply the Newton method. Okay? So this is a standard trick when we want to maximize a concave function using those methods which we have learned in the previous lecture. Okay, next question. We have seen that gradient descent methods are iterative methods, for which we need some kind of stopping criterion. And we have seen various stopping criteria, and we said that the first one, where we essentially stop the iterations where the gradient is small, that's what this says, is preferred over the second criterion, which compares the function values at 2 consecutive iterations. What was the argument? Why do we prefer this stopping criterion over this one?
Because we use it to set 2 other functions, only the gradient, but also the function.
Okay, so
maybe depend on state size.
That's also true. But here, essentially it's 2 things. I mean, it's those 2 answers combined. The first one is that this stopping criterion using the function values requires more knowledge. Essentially, our optimization algorithm also requires to know what is the function value, what is the function to be minimized. While the iterations themselves and this first stopping criterion only requires the gradient. Okay, so we need more knowledge in the second criterion, and it also takes more time because we also need to evaluate the function. Okay, so it's those 2 things combined. So that's why in general we prefer the stopping criterion based on the gradient of the function. Možeš to zastavit.